I want to talk about symmetry, symmetry tests. Somewhat bothered by this topic because, well, I don't know if I should be bothered by it, but it represents a limitation of algebraic approaches to things, which I think is interesting in its own right. It's an application of some of the even and oddness of sine and cosine that we've worked on. So I think that's one of the reasons why it shows up, even though there's limitations to it. So let's just, again, remind ourselves about some symmetry ideas. This is a standard XY plane. Say we've got a parabola, right? The parabola has horizontal symmetry. And it's horizontally symmetrical because we get this sort of flip. If we think of this as a mirror, the right side and the left side are exactly the same. So we would have, in Cartesian terms, we would have the fact that XY is matched by negative XY. So how does that show up in polar coordinates? Well, it's a little more complicated because there's no easy way to get this point over here, no one step way to get it over here. But, and in fact, this is kind of the most complicated one in terms of polar symmetry. Let's do an easier one with vertical symmetry. Shape in the Cartesian plane, and no functions have vertical symmetry in the Cartesian plane. So you don't really actually talk about that symmetry very much. Of course, if we said instead of a function like y equals x squared, which has this horizontal symmetry, because if you put in a negative input or positive input, you still get the same y value out. We could just the same say x equals y squared, and this has vertical symmetry. It's a parabola looks like this, and in this situation we have the same x value, but we get that negative y value. So this is, again, not a function because of that violation of the sort of functionality principle where one input is supposed to give me one output. But in the vertical symmetry is very easy to map to polar coordinates because all we have to do is think about having a point here, r theta, and then having a matching point down here. We can have the same r value, it's the same distance away, but we would just go in the negative theta direction, right? So instead of going this positive theta direction, we go negative theta direction. So the first symmetry test, vertical symmetry, can be tested for by theta being replaced with negative theta. If r is the same as the original, we know there's vertical symmetry. Okay, so the thing that's kind of disappointing is that the converse conclusion is not true. We can't conclude that if r is not the same, we know there is not vertical symmetry. It just means that we have an inconclusive result, which means it may not, or may not have vertical symmetry. I'll show you some examples of that. So that's the first test, is theta replaced with negative theta, and that's vertical. The second test is r being replaced with negative r. This is polar symmetry, because what happens is I have a point, r theta, and I'm plugging in negative r theta, and I want that also to be a point. And so I would see that that comes out the other side, and I would have this point negative r theta. So if I rotate this 180 degrees, I end up with polar symmetry. That's a little harder to, well, we do that test in functions. So for instance, sine has odd symmetry, right? So let's see, y, let's use function notation. F of x equals sine x. No, let's use y and x. So we know that this has rotational symmetry, because if we take this and we spin it around 180 degrees, we get back to the same point. And that's because every point here is matched by a point over here. Every point here is matched by a point over here. Okay. So then the last type of symmetry is the horizontal symmetry, and that is where we replace both. And so that's what I was kind of getting at. We started r theta. If we move this down to r negative theta, that takes us here. But if we take negative r negative theta, then that takes us over here. And that's the test for horizontal symmetry. Okay. So I'll show you a few easy examples, and then we'll look at some more complicated examples. So let's start with r equals 3 sine theta. Let's take a look at it, and then we'll do the actual analysis. Okay, so r equals 3 sine theta. All right, so this is just a little circle. It's got a, I think it ends up with a diameter of 3, so the radius is actually 1.5. We can see clearly that it has horizontal symmetry. So let's do that test and see that that comes up as a positive result. So we're looking at horizontal symmetry. So I'm going to substitute, just a different color here. I'm going to substitute r with negative r, theta with negative theta, and see what happens. Negative r equals 3 sine negative theta. How do we clean it up? Well, we know that the sine of negative theta is equal to negative sine theta, so that negative escapes. And now I can just multiply both sides by -1. So r equals 3 sine theta. Same thing I started with. That proves that there's vertical symmetry. Horizontal symmetry. Okay, let's look at another one. Let's change that to 3 cosine theta. That was a fun one. Look at that. Spiral. Woo! Graphs can be pretty fun. Okay, sorry, I zoomed out quite a bit. Let's get back in here. All right, definitely has vertical symmetry. Let's prove it. So with vertical symmetry, we're just going to replace theta with negative theta. So r equals 3 cosine negative theta should end up being the same. And of course it is, because cosine negative theta is the same as cosine theta. So we ended up back where we started. Okay, so now let's get into some of the sort of murkiness. Just make something up here. 3 plus, I'm not super into, you know, like if you go look up types of, well, here, we've got Google right here, types of graphs. And in the textbook 10.4, it's got all kinds of, look, summary of curves. You got cardioids, and you got inner loop limacons and lemniscates and Bose curves. Not into all that. I mean, not into like you knowing the names of things. That seems irrelevant to me. If you were going to go deep into this field, then yes, you would do all kinds of fun classification projects. So let's see, where were we? Here, this guy, 3 plus 2 cosine theta. So looking at this, I can see that it has vertical symmetry. Is it easy to prove? Let's find out. Test for vertical symmetry. Just replace theta with negative theta. Life is good. R equals 3 plus 2 cosine of negative theta. Of course, cosine eats that negative sign, so it ends up exactly the same. So yes, it's easy to prove that this has vertical symmetry. Now, what about switching that around? 3 sine theta. Okay, well, it's got horizontal symmetry. Is it easy to prove that it has horizontal symmetry? Let's find out. Remember, the test for horizontal symmetry is a little more complicated. We've got to put in both negative r and negative theta. So we've got negative r equals 3 plus 2 sine negative theta. Okay, the negative hops out, and I'm going to multiply both sides by -1. Let's take it slow. 3 minus 2 sine theta. So times -1 times -1. This is r equals -3 plus 2 sine theta. Okay, this is not the same as what I started with, because what I started with was 3 plus 2 sine theta. Now I got -3 plus 2 sine theta. But here's the key part, right? That doesn't mean that there is no horizontal symmetry. It just means that our algebraic test was inconclusive. Let's take a look at why it does. So first of all, in Desmos, I can show that r equals -3 plus 2 sine theta ends up exactly the same, right? The red and the black are on top of each other. Here's the red, here's the black, the red, black, same thing. Now, it's not obvious why that should be the case. So there's some nice other things that you can look at here. GeoGebra has some nice tools. This one is a tool that shows the XY version of it. So your X value, your input is your radian measure, and your output is your radius. And so it kind of track through a cycle and see where these points come from. One of the things you have to do with a graph is be able to identify different points on the graph. So for instance, if I were to ask you to graph this in the homework, I wouldn't expect you to be able to create that picture just from scratch. You can use a graphical representation to start, but I would ask you to identify some points on it. So for instance, where is this point coming from? What is that point? Well, let's just do the math. Let's see, this is my 0 radians. I think this is going to be pi 6. This is going to be pi thirds, and this is going to be pi half. So what happens if I stick pi thirds into this function? 3 plus 2 sine of pi thirds. Okay, sine pi thirds is square root of 3 over 2. So this is 3 plus 2 times square root of 3 over 2. So this ends up as 3 plus the square root of 3. Now, it's a little bit hard to see. It's between 4 and 5, and it's closer to 5 than it is to 4. Right? You understand why I'm saying that? I'm looking at the x-axis there to try to track. This is my 4 circle, right? Which tracks through there. This is my 5 circle. So I'm somewhere between the 4 and the 5 point for my radius. So what's 3 plus the square root of 3? Yeah, it's 4.73. That makes sense for where I'm located, right? So you would be able to locate this point as 3 plus the square root of 3 comma pi thirds. That's the polar coordinate of that point. Right, let's do another one. This one out here looks like a kind of a nice one. So We've gone full pi here. This is going to be 7 pi 6. That's a terrible color. So what happens at 7 pi 6? We got 3 plus 2 times 7 sine 7 pi 6. Or 7 pi 6 is going to give me a y value of -1/2. So 3 plus 2 times -1/2. So it's really 3 minus 1, which is why we end up at 2. And yes, that's exactly right. This is the circle for 2, as you can see, because it tracks back around to here. And my direction here is 7 pi 6. So, sorry, I got a little distracted. We were talking about symmetry. But it is important that you, not that you can create the graph, but that you can identify specific points on the graph and kind of logically connect them to where they are. Now, this is the one that I really think is helpful here. You could use this URL as a way of kind of getting here shorthand. They're not, the URLs aren't too crazy. So this one, I can show them side by side. And again, I can show that this red one is exactly the same as this blue one. This is the 3 plus 2 sine theta and the -3 plus 2 sine theta. And what I like is that it has the blue dot and the red dot on for a specific theta value. So at theta equals 0, of course, we know that for sine 0, that's 0. So 3 plus 0 and -3 plus 0, we start at different places. But as we go around, let's see, how do I turn this on? Press play. Well, I'll just drag it. As I move this around, they're tracking out the same circuit. They're just doing it in a different time. So it's kind of like there's just been a shift. And if we just shifted, say, the red one a little bit forward in time, we would be matching the blue one. I think that's possible to prove algebraically, but it's definitely not within what we care about. So again, for the symmetry tests, the whole point is just to be able to do these 3 tests and be able to say whether you see symmetry or not. If you don't, it doesn't mean there is no symmetry. It just means that the algebraic test is not giving you any evidence of that symmetry. Okay, one more video for 10.4. We'll look at some, solving intersections and minima and maxima, and kind of we'll leave our exploration of polar coordinates there. Polar coordinates are super useful for calculus and very specific applications where there's, movement that's kind of circular, but we're not going to get any deeper than basically where we are now. The next section is really just an application of equation solving using polar functions.